Hello everyone, welcome back to Chem Story. Today we're diving into a really important topic, intermolecular forces. In organic chemistry, knowing what a molecule looks like is only half the story. To really understand how molecules behave in reactions, in solvents, even in biological systems, we need to understand how they interact with each other. That's where intermolecular forces come in. They may be weaker than covalent bonds, but they play a huge role in things like boiling points, solubility, and molecular recognition. So in today's lecture, we'll go over the different types of intermolecular forces, we'll look at what causes them, and we'll see how they affect the physical properties of molecules. Let's get started. Intermolecular forces are the forces that act between molecules, not within them. They help explain how substances behave in different phases, whether it's a solid, a liquid, or a gas. These forces also influence important physical properties like boiling point, melting point, and solubility. Now, the type and strength of intermolecular forces depend on a few key factors, things like molecular shape, polarity, size, and the presence of functional groups. And here's the main idea. The stronger the intermolecular force, the bigger the impact it has on those physical properties. There are three main types of intermolecular forces you should know. First, we have dipole-dipole interactions, which occur between polar molecules. These happen because one molecule's partial positive charge, delta plus, is attracted to another molecule's partial negative charge, delta minus. Next, we have London dispersion forces. These are present in all molecules, even in nonpolar ones. They come from temporary shifts in the electron cloud, which creates a momentary dipole and leads to weak, short-lived attractions. Then there's hydrogen bonding, which is the strongest of the three. It occurs when a hydrogen atom is bonded to a highly electronegative atom, like fluorine, oxygen, or nitrogen. This type of interaction plays a major role in determining boiling points and solubility, especially in water and alcohols. So just to recap, hydrogen bonding is the strongest, dipole-dipole interactions are moderate, and London dispersion forces are the weakest. And these differences help explain why some molecules boil at lower temperatures, and others stay in the liquid phase longer. Alright, let's take a closer look at dipole-dipole interactions. These forces occur between polar molecules, and that's because polar molecules have regions of partial positive and partial negative charge. So naturally, they attract each other. The stronger the dipole moment, the stronger that attraction becomes. Temperature also plays a role in dipole-dipole interactions. At lower temperatures, molecules move more slowly and stay closer together, so the dipole-dipole attraction becomes stronger. But at higher temperatures, the molecules move faster and spread out more, which weakens the interaction between them. Now, let's talk about London dispersion forces. These forces exist in all molecules, but depending on the context, the way we define them can vary a bit. In the broad sense, dispersion forces refer to the weak intermolecular forces present in all molecules, whether they're polar or nonpolar. Because electrons are always moving, they can create temporary dipoles, and that leads to these weak, momentary attractions. This broader definition is what you'll often see in physical chemistry, but in the narrow sense, dispersion forces are usually described as the main intermolecular force in nonpolar molecules. Since nonpolar molecules don't have permanent dipoles, they rely entirely on dispersion forces to stick together. This is the way organic chemistry tends to focus on them, especially when we're talking about things like alkanes or hydrocarbons. Now, both definitions are valid, but the broader one applies more generally across all types of molecules. Still, in organic chemistry, we often stick to the narrow definition when we're dealing with nonpolar compounds. London dispersion forces come from what we call induced dipole interactions. Here's how it works. When the electron density in a nonpolar molecule shifts for just a moment, it creates an instantaneous dipole. That temporary dipole can then induce another dipole in a nearby molecule, and this leads to a weak electrostatic attraction between the two. Since these dipoles are constantly forming and disappearing, dispersion forces are short-lived and relatively weak, but they become stronger in larger molecules because bigger electron clouds are more easily distorted. This explains why larger nonpolar molecules tend to have higher boiling points than smaller ones, even though none of them have permanent dipoles. A good example of this is chlorine molecules. Cl2 is nonpolar because the two chlorine atoms share electrons equally. But at any given moment, the electron distribution can shift just a little, creating a temporary dipole. That temporary dipole can then induce another dipole in a nearby Cl2 molecule, and that leads to weak attractive forces between them. Now, even though these forces are weak, they're still strong enough to affect physical properties, like boiling point and melting point. The strength of London dispersion forces depends on two main factors: molecular size and shape. Larger and heavier atoms or molecules tend to experience stronger dispersion forces than smaller ones. That's because their valence electrons are farther away from the nucleus, so they're not held as tightly, and that makes the electron cloud easier to distort. Since their electron clouds are more easily distorted, larger molecules can form temporary dipoles more readily. That's why molecules with higher polarizability experience stronger dispersion forces. Now, what exactly is polarizability? It refers to how easily an atom or molecule's electron cloud can shift, especially in response to an external electric field. The more easily the electrons can move, the more strongly temporary dipoles can form, and that leads to greater intermolecular attraction. London dispersion forces are also influenced by molecular shape. Even if two molecules have similar molecular weights, a linear molecule usually experiences stronger dispersion forces than a spherical one, and that's because it has more surface area. More surface contact means stronger intermolecular interactions, which leads to stronger dispersion forces, and that can significantly affect physical properties like boiling point, melting point, and viscosity. Among the three types of intermolecular forces, hydrogen bonding is the strongest. This is a special kind of dipole-dipole interaction, and it happens when a hydrogen atom is covalently bonded to fluorine, oxygen, or nitrogen, all of which are highly electronegative elements. Because these atoms pull on electrons so strongly, the hydrogen atom ends up with a noticeable partial positive charge, delta plus. That makes it easy for hydrogen to interact with lone pairs on nearby electronegative atoms, and that's what forms a hydrogen bond, a much stronger attraction than regular dipole interactions. Hydrogen bonds are weaker than covalent bonds, but still strong enough to have a big impact on physical properties. Their strength is usually around 5 to 10% of a covalent bond, which might sound small, but it's more than enough to affect things like boiling point and solubility in a major way. A classic example is water, H2O. In liquid water, each molecule can form hydrogen bonds with its neighbors. The oxygen atom carries a partial negative charge, delta minus, while the hydrogen atoms carry partial positive charges, delta plus. And that charge separation leads to strong intermolecular attraction between water molecules. Hydrogen bonding involves two key players, the hydrogen bond donor and the hydrogen bond acceptor. The donor is a molecule that has an acidic hydrogen, usually one that's covalently bonded to fluorine, oxygen, or nitrogen. Because hydrogen is so highly polarized in these bonds, it can participate in strong hydrogen bonding with other molecules. On the other side, the acceptor is a molecule that has a lone pair of electrons that can interact with that acidic hydrogen. Oxygen, nitrogen, and fluorine are common hydrogen bond acceptors because their lone pairs are positioned just right to form strong hydrogen bonds. So for a good hydrogen bond to form, you need a highly polarized hydrogen from a donor and a lone pair on an electronegative atom from an acceptor. The strength of a hydrogen bond depends on the electronegativity of the atom that hydrogen is bonded to. Stronger hydrogen bonds form when hydrogen is attached to a more electronegative atom. Among these, fluorine forms the strongest hydrogen bonds, followed by oxygen and then nitrogen. Hydrogen bond strength also increases when the hydrogen donor has a higher partial positive charge. That's why hydroxyl groups tend to form stronger hydrogen bonds than amine groups, since oxygen is more electronegative than nitrogen. Another factor is the geometry. Hydrogen bonds are strongest when they're arranged in a straight line. A linear hydrogen bond allows for maximum electrostatic attraction, which makes it more stable and stronger. All right, that wraps up today's lecture. We explored the types and characteristics of intermolecular forces, and we looked at how they influence molecular behavior, from boiling points to solubility and more. Understanding these forces is essential when it comes to predicting chemical and physical properties. Thanks for your attention, and I look forward to seeing you in the next class.